WPR number 10. Okay, write a quadratic equation such that the sum of its roots is 6 and the product of its roots is negative 27. Okay, so the sum formula is negative b over a, the product formula is c over a. In both cases, a is 1, negative b is 6, which means b is negative 6, and c is negative 27. So when we write our quadratic equation, or quadratic equation, it would be 1x squared minus 6x minus 27. Rationalize the denominator. Rationalize means to make rational. Square roots, if they're not perfect squares, are irrational numbers. So rationalizing the denominator means to get rid of the square root in the denominator. And we do that by multiplying by the conjugate. In this example, the conjugate would be found by taking the negative and making it positive. We always just change the sign in the middle. So if I'm going to multiply the denominator by 5 plus square root of 7, and I also need to multiply the numerator by 5 plus square root of 7. I'm double distributing in the numerator and the denominator. In the numerator I'll get 25 plus 5 square root of 7 plus another 5 square root of 7 plus radical 7 times radical 7 is just 7. In the denominator, I'll get 25, but I'll have a positive 5 radical 7 and a negative 5 radical 7, which are opposites and add up to 0. And then I'll have a negative radical 7 times a positive radical 7. So a negative times a positive is a negative, and radical 7 times radical 7 is 7. I can simplify the numerator into 32 plus 10 radical 7, and the denominator would be 18. Each of these terms is divisible by 2, so 16 plus 5 radical 7 over 4. The directions say to factor, not solve, so I'm not going to set this equal to 0 and solve to get a number. Instead, I'm just factoring. This is a tricky trinomial. 12 times 3 is 36, and I list my factors of 6 until I get a pair that can make a 5 by adding or finding the difference. 9 and 4 are different by 5, and I can use them to make my negative 5. So when I rewrite the trinomial, the 12a squared stays the same, but to get the negative 5, I will need a negative 9 and a positive 4, but I also need the AB, so I'll have a negative 9AB plus 4AB, and the minus 3b squared is also part of this. Okay, so now I'm going to separate this into two problems and factor each part by GCF. So from the 9 and the 12 I get a 3, and from the a squared and the ab I get an a. And when I divide each of those terms by 3a, I will have 4a minus 3b and in the second pair of two terms I can factor out a GCF of b, and I'll be left with 4a minus 3b as well. that means that I've done it right, the fact that I have a 4a minus 3b in both. And so this term and this term have a common factor of 4a minus 3b. So I'm going to factor out the 4a minus 3b. And when I factor 4a minus 3b out, I'll be left with 3a plus b. Again, I'm not setting these equal to 0. The directions just said to factor. Okay, in question 3b, the directions are to express product as a trinomial. Express means write. Product means the answer to a multiplication problem. So we're going to go ahead and multiply this, and we'll worry about what it means to write it as a trinomial after we multiply it out. Now, because I'm multiplying a binomial by a binomial, that means that I have to distribute the 1/2 y squared onto the 12y and 3/5, and also doubly distribute the negative 1/3 y onto the 12y and the 3/5. So I'm going to go ahead and write that out here. So I have the 1/2 y squared times the 12y plus the 1/2 y squared times the 3/5. So I'm done distributing the 1/2 y squared. Now I need to distribute the negative 1/3 y onto the 12y and the 3/5. Okay, now I'm going to multiply the 1/2 y squared by the 12y, and I need to multiply the fractions first. 1/2 times 12 is 12 halves, or 6, and y squared times y is y cubed. Then I have a 1/2 times 3/5, which will give me 3/10, and there's just a y squared there, not being multiplied by anything else, so it doesn't change. Next I have negative 1/3 times 12, which would be negative 12/3, or negative 4. And lastly, I'll have negative 1/3 times 3/5, which would be negative 3/15 y. Now, the answer, or the directions I should say that we should express as a trinomial, but we have 4 terms, which is not a trinomial. But that's okay. We can take these two middle terms, which have the same variable to the same power, therefore they're like terms. We can combine those. So I'm going to have a 6y cubed. And now I have this 3/10 minus 4. So I need to get a common denominator, which would be 10. So the 3/10 is fine the way it is. But I need to subtract from that 4. Well, if I make the denominator of that 4 10, that means I really multiplied the denominator by 10. And I need to multiply the numerator by 10. So it looks like I'll get negative 37 over 10, so I'll have a negative 37 over 10 y squared. That can't be reduced, but this 3/15 can. 3 goes into each of them 1 and 5 times, so I'll have minus 1y over 5. This is called a complex fraction. Well, it doesn't look like a complex fraction yet, but we have to rewrite this as 1 over y to the power of positive 1, and this is 1 over x to the power of positive 1. So it's going to end up looking like this. And now what we need to do is we need to multiply the numerator and the denominator by the least common multiple of all of the denominators. So this really has a denominator of 1, and so does this. So my denominators are 1 and y and 1 and an x. To get rid of all of those, I would need to multiply the numerator by the same thing as the denominator. And that's the least common multiple, which is xy. So every term is being multiplied by xy over 1. So the x over 1 is being multiplied by xy over 1. And the 1 over y is being multiplied by the xy over 1. And the y over 1 is being multiplied by the xy over 1. And lastly, the 1 over x is being multiplied by the xy over 1. Now I can multiply each of these fractions. The purpose here is to get rid of all of the denominators. So in this first example, or this first part of the problem here, nothing cancels, so I just have this x times xy, which would be x squared y. But then, over here, the y cancels the y in the numerator, and I'm just left with 1 times x in the numerator, which is x. And so now you can see it worked. We got rid of the denominator, and now we can work on the bottom of this complex fraction. And again, we're going to see that nothing cancels, so we're left with xy squared. But in the second part, the x's cancel, and I'm left with, you can hardly see it, but there's a y over there. Now, this answer is not our final answer because these can be factored, and whenever possible we need to factor to see if we can cancel or reduce. So in the numerator there's a GCF of x, and when I divide those two terms by x, I'd be left with xy plus 1. And in the denominator there's a GCF of y, and when I divide those, I'm left with also xy plus 1 when I divide by each of those by y. And so these like factors reduce to 1s, so I have in the numerator x times 1 and the denominator y times 1, and that's as far as I can take this.